For thousands of years, comets blazed across the skies as symbols of mystery, awe, and fear. To ancient eyes, they were omens of change, but today they are more than streaks of light. They are time capsules, carrying secrets from the birth of our solar system. In this episode of Cosmic Compass, we're not just watching comets pass by, we're chasing them, colliding with them, and even bringing pieces of them back to Earth. Together, we'll follow the story of two extraordinary missions, Stardust and Deep Impact, and discover how they revealed the true nature of comets, and perhaps even clues to the origins of life itself. If you've ever gazed up at the night sky and seen a comet streak past, you will know the sense of wonder it inspires. For much of human history, comets were feared as omens, bright-tailed messengers thought to bring change or disaster. But in the last half-century, the roles have shifted. These ancient wanderers are no longer just visitors to us. Now we have found ways to visit them. Scientists had long wondered about the true nature of comets. Where did they come from? How were they formed? Were they time capsules from the birth of our solar system, or visitors from beyond? In the 1980s, probes gave us our first close-up photos of Halley's Comet, but to truly understand what comets are made of and what role they might have played in our origins, scientists needed to go further. They needed to touch, to capture, and even to strike. Two bold missions rose to meet that challenge. One would gently collect dust like a cosmic butterfly net and bring it home. The other would take a more dramatic approach, colliding head-on with a comet, exploding with the force of tons of TNT. And by chance, both missions would converge on one small, mysterious body, Comet Tempel 1. So let's explore the explosive story of Tempel 1 and how two spacecraft, Stardust and Deep Impact, changed forever what we know about these icy nomads of the solar system. By the early 1990s, comets were still cloaked in mystery. A handful of missions had given us tantalizing glimpses. In 1986, no fewer than 5 spacecraft from Europe, the Soviet Union, and Japan raced to meet Halley's Comet. They captured extraordinary images of its nucleus and streams of dust. Other comets, like Giacobini's Zinner and Grieg's Schellerup, had also been visited. But these missions were all flybys, and the closest approaches were still hundreds of kilometers away. From those distances, scientists could photograph the coma and tail and even collect some particles, but the real secrets remained hidden beneath the surface. What was inside a comet? Was it a solid ball of ice? A loose rubble pile of dust and frozen gas? And where had they formed? To answer those questions, scientists realized they would need to probe deeper. Looking at the surface was not enough. They would need to find a way to peer inside. That was when an ambitious idea began to take shape. In 1999, NASA approved one of its most daring cometary projects. The idea was simple, though dramatic: smash a spacecraft directly into a comet at high speed, create a crater, and analyze what spilled out. From the energy of the impact and the resulting crater size, scientists could deduce whether the comet was made of dense solid ice or soft fluffy material. The target chosen was Comet Tempel 1, a short period comet with a nucleus about 8 kilometers long and 5 wide. Tempel 1 wasn't a household name like Halley, but it had the perfect orbit for the mission. The spacecraft itself, named Deep Impact, was built in 2 parts. The larger flyby craft carried scientific instruments, the high-resolution imager, the medium-resolution imager, solar panels, and a debris shield. Its smaller companion, the impactor, would be released to collide with the comet. This impactor, though, only 372 kilograms, would be travelling at over 37,000 kilometers per hour, delivering a kinetic punch equal to 5 tons of TNT. There was even a public element. NASA invited people around the world to send their names, which were etched onto a disc aboard the impactor. Over 600,000 names journeyed toward Tempel 1, destined to crash into its surface. and in a stroke of poetic timing, the collision was scheduled for July 4th, 2005, America's Independence Day. Whether for scientific clarity or patriotic fireworks, the symbolism was powerful. But ambitious missions rarely go smoothly. Just a day after launch in January 2005, Deep Impact's onboard computer shut down into safe mode, alarming engineers. It turned out to be a minor programming issue. The spacecraft thought its thrusters were overheating, when in fact they were within limits. With a quick fix, Deep Impact was back on course. After 6 months and 429 million kilometres of travel, Deep Impact finally approached its quarry. The impactor was released from the flyby, lining up its fatal trajectory. On July 4th, at almost the exact predicted second, the impactor slammed into Tempel 1. The collision was spectacular. The impact produced a flash brighter than anyone expected, briefly lighting up the comet's surface. The energy released, nearly 20 billion joules, was immense. Around 5 million kilograms of water and as much as 25 million kilograms of dust were blasted into space. But success came with a twist. The very dust cloud the scientists had created was so thick that it obscured the flyby's view of the crater. Deep Impact had delivered its punch, but the main evidence, the shape and size of the crater, was hidden behind a veil of debris. For 13 days, dust outgassed from the comet, making imaging nearly impossible. It was both triumph and frustration. We knew Tempel 1 was porous, rich in ice, and prone to outgassing, but we still lacked the definitive view inside. It was like tearing open a wrapped present, only to be blinded by smoke before seeing what was inside. Another mission would be needed to finish the job. Fortunately, another spacecraft was already out there. Years earlier, NASA had launched Stardust with a very different goal: to collect actual particles from a comet and bring them back to Earth. Launched in 1999, Stardust was aimed at Comet Wild 2. The challenge was immense. Comets race through the solar system at speeds up to 160,000 kilometers per hour. Stardust would meet Wild 2 at a relative velocity of over 6 kilometers per second. At those speeds, capturing even tiny particles is like catching bullets. To solve this, Stardust carried one of the most remarkable materials ever created: aerogel. Aerogel is over 99% air translucent, and so light it seems unreal, and yet it can gently slow down high-speed particles, leaving behind trails like meteor streaks. This allowed Stardust to capture samples without destroying them. In 2004, Stardust flew by Wild 2. What it saw shocked scientists. Far from being a bland, cratered potato, Wild 2's surface was alive with activity. Towers and pinnacles, hundreds of meters tall, jutted upward. Cavities vented jets of dust, even from the comet's dark side. Most surprising of all, there were virtually no impact craters. Unlike the Moon or Mars, the comet's surface seemed to renew itself, erasing scars in mere geological moments. Stardust's aerogel trays caught thousands of dust particles, storing them in a capsule that was returned to Earth in 2006. When scientists opened it, they found wonders. The dust grains were not alien to our solar system, but born within it. Some had been forged in searing heat chondrules and calcium aluminum inclusions materials that form at thousands of degrees. This was shocking because comets had always been thought of as icy relics from the cold outer reaches. Clearly, their building blocks had once been fire as well as ice. Most extraordinary of all among the samples was the amino acid glycine, one of the building blocks of proteins and therefore of life. While not evidence of life itself, it suggested that comets may have delivered vital ingredients for life to Earth. Suddenly, comets weren't just icy wanderers. They might be part of our own origin story. After its success with Wild 2, Stardust still had fuel in its tanks. NASA decided not to waste a working spacecraft. Instead, they assigned it a new mission to return to Tempel 1 and finish Deep Impact's unfinished work. This was a unique opportunity. For the first time in history, humanity could revisit a comet years later and see how it had changed. Even more, Stardust could photograph the crater created by Deep Impact, finally revealing what had been hidden behind the dust cloud. But the navigation challenge was daunting. Tempel 1 rotated once every 40 hours, and Stardust would arrive years later after multiple solar orbits. Engineers had to calculate the comet's spin with extreme precision, predicting its orientation to within a single degree a full year before arrival. A single miscalculation could mean missing the crater entirely. On February 14th, 2011, Valentine's Day, Stardust flew past Tempel 1 at a distance of just 181 kilometres. It survived a barrage of tiny dust particles, each impact puncturing its shielding, but the craft endured. As the images returned, scientists held their breath. And then there, it was the crater left by Deep Impact. It measured about 150 metres across, larger than predicted. From this, scientists learned that Tempel 1's surface was astonishingly soft, like powdered snow. In fact, they concluded that the comet was about 75% empty space, held together loosely by gravity. Even more, Stardust revealed surface changes. Cliffs had eroded by dozens of metres. Pits had merged. Tempel 1 was not static, but a world reshaped by each orbit, each heating and cooling cycle. At last, Deep Impact's story had closure thanks to Stardust. The story didn't end there. Deep Impact's flyby craft was repurposed for new work under the name Epoxy, studying other comets and even observing exoplanets before contact was lost in 2013. Stardust 2 kept going until its last drop of fuel was spent. In 2011, after completing its Tempel 1 flyby, engineers let it burn the last of its propellant, testing their models of fuel consumption. When it was finally dry, Stardust sent one last signal and was shut down forever, resting now among the stars it had explored. Together, these missions transformed our understanding of comets. They showed us that comets are not alien intruders from distant stars, but products of our own solar system. They revealed that comets are not inert relics, but dynamic changing bodies. And they offered tantalizing evidence that comets may have delivered the molecules that made life possible on Earth. Comets have always carried a dual image, beautiful yet ominous, mysterious yet captivating. For ancient humans, they were signs from the gods. Today, we see them as messengers from the past, and perhaps the seeds of our own existence. The work of Stardust and Deep Impact proved that with human ingenuity, patience and daring, we can turn cosmic mysteries into knowledge. So the next time you see a comet streak across the night sky, remember, it may be more than just a spectacle. It may be part of the reason you are here at all. And in the end, all it took was to catch the dust from one comet and to punch another really, really hard. From feared omens to scientific treasure troves, comets have always been messengers. Thanks to Stardust and Deep Impact, we now know they are not strangers from distant stars, but dynamic members of our own solar system. They are icy archives of fire and dust and carriers of molecules that may have helped spark life on Earth. Their story reminds us of something profound. By daring to reach out to punch a comet or catch its dust, we bring the universe a little closer to home. If you enjoyed this journey, make sure to subscribe to Cosmic Compass for more stories of planets, stars, and cosmic mysteries. And tell us in the comments, if you could visit any comet yourself, which one would you choose? Until next time, let's keep looking up and keep exploring together.